Hello everyone, in this video I'll explain how you can build a 12V DC to 220V AC modified sine wave inverter using TL494. In the previous video, I showed how you can build simple push-pull inverter using TL494. The link to the simple high-frequency inverter is provided in the video description section below. That inverter is a simple square wave high-frequency inverter and was intended for resistive load only, such as incandescent light bulbs or some specific switching power supplies, like laptop chargers, that can accept high-frequency AC. But the circuit cannot be used and should not be used for other home electrical appliances, because it may damage them. As shown, I have modified the simple high-frequency push-pull inverter into a modified sine wave inverter. To do this, I used the high-frequency inverter with modification as the first stage, and added another low-frequency stage. The two stages together work together to produce 50-60 Hz, 220V AC signal at the output, which makes it safer to use with electrical appliances. The modified inverter operates in two distinct stages. Stage 1, DC to DC boost, generates a high-frequency switching carrier approximately 48 kHz to step up the battery voltage into a stable high-voltage DC rail, 330V. Stage 2, DC-AC inversion, then takes this high-voltage DC and uses a low-frequency timing circuit, 50-60 Hz, to chop the power. By utilizing the dead time control, DTC, of the second stage, TL494, it creates specific gaps between pulses, resulting in a 220V modified sine wave output suitable for AC loads. The addition of the second stage was necessary because the single TL494 IC cannot simultaneously manage the massive voltage boost with ferrite core transformer and the low frequency oscillation required for a 220V AC output. That is, the previous high frequency square wave first stage inverter is used to make the transformer small and efficient. One could use iron core transformer that operates at low frequency, but it would require replacement of TL494 with sine wave generator IC, additional gate driver IC, and the inverter would be heavy and bulky. So we opted to use the same high frequency capable ferrite core transformer. So, to convert my previous TL494 inverter design into modified sine wave inverter, we need to build whole new second stage and make minor modifications to the first stage. I will start by explaining the modification I made to the earlier high-frequency inverter design as the first stage, and then explain how to build the second stage and connect to the first stage to complete the TL494-based modified sine wave inverter. 1. First stage of TL494 modified sine wave inverter design. We have to make the following modification in order to convert the square wave TL494 inverter to first stage of modified sine wave inverter. The sampled voltage from the voltage divider. Let's feed this into the TL494 pin 1 in plus pin. The pin 2 1 in minus pin is used as 2.5V reference by connecting it to a equal value 10k ohm resistor voltage divider from the pin 14 5V ref and ground. The internal error amplifier compares the voltages of pin 2 and pin 1 and automatically widen the pulses if the battery voltage drops or the load increases, keeping the output RMS voltage stable. The feedback implementation to voltage regulation is as follows. First, we set the reference voltage on pin 2 at 2.5V so that the chip has more room to adjust. To do this, connect a 10 kilo ohm resistor from pin 14, 5V, to pin 2, and another 10 kilo ohm resistor from pin 2 to ground, pin 7. Doing this, the pin 2 now sits at stable 2.5V referees. We need to sample the output and connect the voltage feedback from the output back to the input pin. The output is a high DC voltage after the diode bridge rectifier and smoothing capacitor, explained later on. For correct voltage sampling into pin 1, we need to scale the 310V DC down to match that pin 2 2.5V reference voltage. For this, we will create a high resistor value voltage divider circuit, connect a 1.2 megaohm resistor or two 600k ohm in series for safety from the positive high voltage DC bus to pin 1, then connect a 10k ohm resistor from pin 1 to ground. This results in approximately 2.56V at the pin 1 input when the output voltage is 310V, since voltage divider is given by 310V times the ratio of 10k ohm and 1.2 megohm plus 10k ohm. Now, with this voltage divider input, if the output drops due to load, the voltage on pin 1 drops and the TL494 automatically increases the pulse width to compensate. Stabilize the loop compensation. Switching power supplies can hunt or oscillate if the feedback is too fast. To fix this, I've connected a 100 nanofarad capacitor and a 47 ohm resistor in series between pin 3 feedback and pin 2. This slows down the error amplifier just enough to keep the voltage steady without jittering. These two Feedback and compensation circuit are the modification required for the TL494 of the previous high-frequency inverter circuit. C. Diode rectifier and smoothing capacitor. The output of the ferrite core transformer used in earlier design is a high-frequency, high-voltage pulse signal. This output must be converted to high-voltage DC, around 310 volts to 340 volts DC first. To do this, we have to add bridge rectifier and a filter capacitor. The bridge rectifier. We need to add a full bridge rectifier to transformer TR1. We cannot use standard 1N4007 diodes here. One must use ultra-fast recovery diodes, like the UF4007 or HER308, because standard diodes are too slow for high-frequency switching and will overheat. I've used UF5406 diodes here. The filter capacitor. I added a high-voltage electrolytic capacitor after the rectifier, 47 microfarad to 100 microfarad. I used 100 microfarad and give a stable DC bus. The output of this capacitor is connected back to the first stage TL494 pin 1 for feedback voltage regulation, as previously mentioned. D. The Snubber circuit, protection and stability. I have added the RC Snubber circuits with 10 ohm resistor and 10 nanofarad capacitor between the drains of the upper half and the lower half power stage and the ground. This Snubber circuit serves as a critical safety net for IRF Z44N MOSFETs. The reason for adding them is that when the MOSFETs Q3 to Q6 are switched off, the magnetic field in the transformer primary collapses. This creates a massive inductive spike back EMF that can exceed the 55 volt limit of the IRF Z44N MOSFETs. The Snubber circuit snubs or absorbs this high voltage energy, protecting the MOSFETs from internal breakdown and heat failure. Another reason is to improve the output stability. As you'll perhaps notice in the physical build, the DC output can sometimes bounce or oscillate. The Snubber helps by stopping high-frequency oscillations, noise, on the primary side that can confuse the TL494's feedback loop. Also, it helps by turning the sharp, chaotic spikes into smooth curves, making the physical circuit more efficient. Some points on R&C component selection you need to be aware of. I've used a 10 nanofarad capacitor. The reason is it acts as a high-frequency bypass, capturing the energy of the spike. This should be a high-voltage ceramic or film capacitor and rated 100 volts or higher. Similarly, I've used 10 ohm resistor. This resistor dissipates the captured energy as a tiny amount of heat. This should be a 2W resistor to handle the constant switching stress. Second stage of TL494 modified sine wave inverter design. The second stage circuit is completely new and added to the previous inverter design. This consists of another TL494, 2 IR2110 MOSFET driver IC, 4 IRF840 N-channel MOSFETs, among other smaller components like diodes, resistors, capacitors. While the first stage generates high-frequency square wave and outputs high-voltage DC output, the second stage is designed to generate 50 to 60 Hz low-frequency signal and chops the high voltage from the first stage into 50 to 60 Hz 220 volt modified AC sine signal at the output. Now I will explain the second stage circuit in more details. Dead time control, DTC. To convert the TL494 push-pull square wave inverter into modified sine wave inverter, we need to adjust the dead time. Usually the TL494 generates square wave, whose frequency is set by the capacitor CT pin and resistor pin RT, above 20 kHz, and each side is of the MOSFETs are on for 50% of the cycle. A modified sine wave introduces a dead zone where both sides are off, creating a stepped waveform. 0 volt to positive peak, then back to 0 volt, then going to negative peak and back to 0 volt. This is much easier on sensitive electronics than a raw square wave and is achieved by adjusting the dead time control, DTC, on pin 4. For this, we need to apply a small positive voltage to pin 4. To do this, we can use a voltage divider between the 5 volt reference, pin 14, and ground, pin 7, and connect the junction to the pin 4. A true modified sine wave usually has the MOSFETs on for about 70% to 75% of each half cycle. To achieve this, we will use a 10K potentiometer and adjust it so the pin 4 receives roughly 0.5 volt to 1.5 volts. Increasing this voltage narrows the pulse width, creating the stepped gap of the modified sine wave. B. Frequency adjustment. Our sine wave inverters usually operate at standard grid frequencies 50 Hz or 60 Hz. For a 50 Hz output in push-pull mode, the TL494 internal oscillator needs to run at 100 Hz. The frequency is determined by the equation frequency of oscillator equals to ratio of 1.1 divided by RT times CT. Here I have used 1 microfarad electrolytic or film capacitor C13 connected to CT pin 5 and resistor value by combining 10k ohm R28 in series with a 5k ohm potentiometer RV2 in a more manageable range, around 10k ohm to 15k ohm. C. Adding the modified sine stage, H-bridge, to get 50 Hz AC out from 310 volt DC bus from the first stage, we need an H-bridge. The H-bridge is made up of 4 more MOSFETs rated for 400V or higher, like the RF840, arranged in an H pattern as shown. The TL494, which is set to 50 Hz, is used to drive this H-bridge. By using the pin 4 dead time control trick we discussed earlier on the second TL494, you create the modified sine steps. The snubber circuits for load protection, and the AC output, the RC snubber, is placed directly across the live and neutral terminals. Its primary job is to protect the H-bridge from the kickback of real-world appliances. That is, it protects the H-bridge MOSFETs when driving inductive loads like fans, motors, or transformers by absorbing high voltage spikes caused by the 50 Hz switching. It also filters noise by rounding off the sharp edges of the modified sine wave, reducing electromagnetic interference, EMI, and preventing ghosting in electronic devices. You can use a resistor of 100 to 220 ohms rated 3 watts to 5 watts. I used 100 ohms. Similarly, you can use a 10 nanofarad to 47 nanofarad capacitor and must be rated for 630 volts. Here I used 47 nanofarad. That's it. This is how I converted my TL494 simple square wave inverter circuit design into modified sine wave inverter. In the next video, I will show through simulation and animation how this circuit works. I will show the output of each stages, how feedback for voltage regulation works, signal waveforms, and frequency spectrum. So do subscribe. Also see the earlier video on the simple push-pull high-frequency TL494 inverter, which will help you understand this video. Thanks for watching. See you in the next.